Hey guys, we're going to do section 1.6 today. Before you watch the video, I would like for you to pause right now and try this warm-up. And then I'm going to go ahead and put the answers up. So pause the video now and try it on your own and start again when you are finished. So for this warm-up, you are going to first take the limit as x approaches -3, plus means from the right side. So as I'm approaching -3 from the right side, my limit is approximately 3. For number 2, when I come from the left side of -3, my limit is -1. For number 3, take the limit as x approaches 4. It does not specify the side, so that means you're going to come from both directions. And from both directions, your limit is approaching -3. Number 4, take the limit as x approaches 0. So I'm approaching 0 again from both directions, and that looks like +3. And then the last question is find f of 4. That means what is the y value when x is 4? So the y value is actually this filled in circle here, and that is at 1. Okay, today's lesson is limits involving infinity, and this is actually the last lesson in chapter 1. So next week you're going to begin reviewing the whole chapter, and you'll have a test at the end of the week. So in this lesson, we're going to spend a lot of time discussing asymptotes. And so what that means is we're going to be able to describe an asymptote and a graph using limits. So I want you to start with these pictures that you see here on this slide. Make sure that these make sense to you. Okay, so these blue lines represent asymptotes, which is just an imaginary line that your graph is never going to cross. So hopefully it makes sense to you that if I were to describe this picture with limits, I would describe it as x is approaching a is just some number, from the left side. And the limit is going up to infinity forever, right? Sometimes we call that d and e, but in this case, we're going to call it infinity because it's going up. So the case is, if I have a limit as I'm approaching some number, and I get that the limit is equal to infinity, then I can assume that there is an asymptote there, because asymptotes are the only thing that make your graph kind of go up or down to infinity rapidly like this. So example B over here is just the same kind of thing but flipped, showing that you can have an asymptote coming from the right side as well. And then these two down here are just showing that asymptotes could also make your graph turn and go down forever. So essentially everything that you see on this slide, they all have that same statement in common, that when you take the limit as you're approaching some number, if you get infinity or negative infinity as your outcome, you can assume that there is an asymptote in that location. So here's your statement. Your statement says that the line x equals some number is called a vertical asymptote of the curve if at least one of the following statements is true. And you can see that all of these statements are just saying that as I'm approaching the number, my limit is equal to either infinity or negative infinity. And that can be coming from both directions or even just from one side. So we are going to do a couple of limit problems, and then we're going to make a statement saying what that means in relation to the way the graph looks. So we are going to start with taking the limit as x approaches 3 from the right side for 2x over x minus 3. Now what we would have done in the past is we would have just done plug and chug, right? But in this case, plug and chug is not going to work because then you would get 0 in the denominator. Okay, so instead what I'm going to suggest you do is I'm going to suggest that you do more of a hypothetical plug and chug. So in this case, we're approaching 3 from the right side. So that would be like coming from 5, 4, 3, and down that way. So I'm going to pick a number that's really, really close to 3, but is on the positive side of 3. So the first thing that comes to mind is like 3.1. And then I'm going to ask you to kind of see what would happen if you plugged in 3.1. Okay, so this is not the correct way to write your answer. This is just you mapping out your thoughts. Okay, so what would happen if you plug in 3.1? Well, the top you would get 6.2, and the bottom you would get 0.1. And if you divide, that would give you 62. Okay, again, 62 is not the answer. But what I'm going to do is now compare that to if I got even closer to 3. So maybe I call it like 3.01. Okay, so I'm going to put a 0 to make it a really small number or a number that's really, really close to 3. So what would happen if this was 3.01? Well, you would get 6.02 on the top, and on the bottom you would get 0.01. And that would give you an answer of 602. Okay, so there's not going to be a single answer like a numerical value you're going to come up with, because what's happening is this number that we're plugging in is getting closer and closer to 3 as the limit continues. So essentially what's going to happen if we summarize what we see here, we're going to have a number on the top that's pretty close to 6, right? But what's going to happen to this number on the bottom the closer we get to 3? This number is going to get infinitely small. So it's going to be a really small number. Okay, a really small number. So what happens if you take a number like 6, or really you could pick any number you want. What happens if you divide by a really small number? Well, that's like the same as multiplying by a really big number. Okay, so if you're dividing by something that's really, really small, it's going to make your answer really, really big. Okay, it's going to make your answer some really big number. Okay, and if we find that our answer is going to be some really big number, we would call that infinity. All right, let's do the other limit, and then we will write a statement to say what this actually means. By the way, I'm going to go clean this up. So if I was doing my work, I could think through it, all of my work with all this stuff that's shown here, but I want to go back and make sure that I answer the question and just say that that would be infinity, okay? All right, so we're going to go through the second example in a pretty similar manner. So we're going to say, okay, plug and chug would be ideal, but it will not work in this case. So let's think through it logically. So I'm going to pick a number really close to 3, but this time we're approaching from the left. So that means we're going to plug in something that's smaller than 3, but really close to it. So I don't know, maybe you want to start with like 2.9. The top is going to be, I don't know, what, 5.8. The bottom is going to be negative 0.1 in this case. And if you divide those, you would get negative 58. Okay? Keep going and pick a number that's even closer, like 2.99. So when you do the math, the top is going to be some really small number, or not really small number, some number really close to 6. The bottom is going to be negative 0.01, which would give you negative 600. So do you see what's happening? The smaller the number that gets closer to 3, my solution gets even larger, but in the negative direction. So the general consensus here is that if I take 6 divided by some small, very small negative number, I am going to get an answer that is a big, really big negative number, right? Negative number. And that is going to be equivalent to negative infinity. Okay, so what does this mean? Go back and look at your theorems on the last slide. This is going to basically tell us that we have an asymptote, okay? We have an asymptote because the closer I get to 3, the larger my numbers get. When I'm coming from the right side, we're getting closer to infinity. And when I'm coming from the left, I'm getting closer to negative infinity. So if you kind of want to draw a picture to help you, and this is by no means an accurate drawing, but just the general shape, that means we have an asymptote here at 3. And the closer I get to 3 from the right side, the bigger the numbers get. So it'd kind of do one of those. And as I approach 3 from the left, I have a graph that's going down. That's supposed to be closer, but you get the point. Going closer and closer to 3, I get a graph that goes downward to negative infinity. So we're going to make a quick statement here that says that we have a vertical asymptote at x equals 3. Okay. Here is a picture of the function. Hold on a second. I think I skipped a slide. Here's a picture of the function x squared minus 1 over x squared plus 1. So when you look at this, hopefully you see that there is an asymptote occurring, but it's not like a normal one. So I'm going to get my dotted line drawing here, and I'm going to draw an asymptote right here. So you might want to do that on your paper as well. There is an asymptote, but a horizontal asymptote occurring in this function, okay? And it looks like it is right around y equals 1. Okay, so there's an asymptote at y equals 1. Now, remember, in this lesson, we're trying to work towards identifying asymptotes, but we want to do so using the concept of limits, because that's the whole theme of this chapter. So here is something that we could say. We could say that the limit as x approaches infinity, which would mean follow your graph all the way to the right side, it looks like it's leveling out at 1. And the same thing goes for negative infinity. So graphically, that means if I were to follow my graph all the way to the right side, it is leveling out at y equals 1, and so is the left side. So if I see a situation where I take the limit as x goes to infinity or to negative infinity, and I get an answer that's a definite number, then I can assume there is a horizontal asymptote in that location, okay? So here's your formal definition here. If I take the limit as x goes to either positive or negative infinity, and I get a number, L just means a definite number, so not like a D&E situation, then you have a horizontal asymptote in that location. Okay. Now, in this example I just showed you, both the right side and the left side approached 1, and so we had just a single asymptote on this graph. However, it won't always look like that. Here is something you may also see. So these are just some other graphs that have horizontal asymptotes, but they look a little bit different. Okay. So please understand that horizontal asymptotes generally cause a graph to level out, but you can cross a horizontal asymptote. So it's a little different than vertical. Like this is like a play on a sine function up here. And it is definitely leveling out as you go towards infinity. It's leveling out closer and closer to that blue dotted line. Okay. You could have a situation where you have a horizontal asymptote, but it only occurs on half of the graph. So in this case, if I said take the limit as x approaches infinity, that's the positive side, or the right side, I should say, you're actually going to get infinity. So that's not going to be an asymptote following the asymptote definition on this right side because it's going up forever. However, if you say what's the limit as x approaches negative infinity, you're going to say it is 0 because the graph is leveling out on the left side. Hence, we have a horizontal asymptote on the left side of our function, just not on the right, okay? Horizontal asymptote at y equals 0. There can be a horizontal asymptote in each direction as well, like this. So you might have one that kind of binds the top of the function and one that binds the bottom of the function. Okay, so what we're going to do here is we are going to identify all the asymptotes in this picture, and we're going to identify them using limits. Okay, so let's start with taking the limit as x approaches infinity. Okay, because if I take the limit as x approaches infinity and I get a number, then that means I have a horizontal asymptote. So if I go to the right side of my graph, my function is leveling out, and that looks like it's around the y value of 4. Okay, so I would say the limit as I go to infinity is equal to 4, which means I have a horizontal asymptote at y equals 4. While we're at it, let's go ahead and take the limit as x goes to negative infinity. So go to the very left side of your graph. That's where x goes to negative infinity. Where does it level out? It looks like it's about a 2. So that means we have another horizontal asymptote at y equals 2. Okay. We have 2 other asymptotes in this problem. They are vertical. So there's one here, it appears, and there's one over here. So what we're going to do is we're going to identify those by limits. Now remember, vertical asymptotes occur when you are approaching a number and the answer of the limit goes to infinity or negative infinity. So I'm going to start over here with this one on the left. This one I would say as x gets closer to -1, and I'm actually not going to identify the side because it's from both sides. As I get closer to -1 on both sides, my graph goes up to infinity on both sides. And so that would fit the qualifications for a vertical asymptote. And that would be identified at x equals -1. Okay, let's go to this one here. I'm going to say let's take the limit as I get closer to x equals 2. But I'll do from the left side first because the left side's not going in the same direction as the right side. So if I take the limit from the left, I am getting a graph that goes down to negative infinity. And when I take the limit as x approaches 2 from the right side, my graph goes up to positive infinity. Now, it doesn't matter that one goes down and one goes up. It still shows that you have a vertical asymptote in that location. Okay? And that would be at x equals 2. Okay, so next we're going to kind of establish a pretty important rule. And this is called the stick of gum rule. It just sounds very strange, but stay with me for a second. Okay, so here's the function. The function is 1 over x. And I want to know what this function will do as x approaches infinity. Now, some of you more logical thinkers are probably going to think back to parent functions because 1 over x is the reciprocal parent function. And maybe you can visualize that in your head and take the limit that way. The rest of you are probably kind of waiting for me to go through and explain this because we haven't learned any limits that how to find limits as we go to infinity. Okay, so here's how I want you to think through this. Let's pretend you have one stick of gum and there are, I don't know, X people in the room, and you're going to share that stick of gum with everybody in the room. Okay, so let's say there are 10 people in the room, and you're going to take that one stick of gum and you're going to divide it into 10 pieces. So everybody's going to get 1/10 of a piece of gum. Now, it's not much, right? But it still counts as having some gum. What if that the room that you're in actually has 50 people in it? And you're really going to be nice and you're going to share that stick of gum with 50 people. If you were even able to take your gum and break it into 50 pieces, the piece of gum would now be so small that you probably wouldn't even be able to chew it, right? Now imagine what would happen if you took that one stick of gum and divided it by, I don't know, 5,000 people. If you were even able to do this, would you even have gum that you could see? Or would it be so small that it almost doesn't exist anymore? Because in my head, it would be so small that I wouldn't even be able to see it, especially if you keep increasing the number of people that you're going to share this stick of gum with, right? So basically what I'm saying is, if you are going to divide by a very large number, your stick of gum by a very large number, you're basically going to end up with approximately no gum, right? So we call this the stick of gum rule because it's a trick. If you can remember this little thought process, it's a trick that helps you with a lot of limit computations when you're taking the limit as you go to infinity, okay? So I am going to, let me move this around and make some space to actually answer these questions. So if I want to take the limit as x goes to infinity for one stick of gum divided by some really big number, because it says x is going to positive infinity, that means that I would be left with almost no gum, okay? Now, would that change if I have, if I'm dividing by a number like negative infinity? So if I take 1 and I divide by a really, really big negative number, is that going to change my answer? No, it's not. I'm still going to get a 0 because I'm basically still dividing by a really big number, which is going to give me a number that is infinitely small, pretty much like 0, okay? Here is the stick of gum rule in a nicer format. So this is the same thing again. Okay. So this next question, I'm going to show you how to do this 2 ways. One way, and the first way, is I am going to show you by using the stick of gum rule to help us. So here's why. Obviously, this looks like a fraction, and the stick of gum rule also looks like a fraction. True? No, it is a fraction. So I know this statement to be true because we just talked about it, and it's kind of like a known fact now, if you will. So my question at hand in example 5 looks like a fraction just like this, and my limit is also being taken as x goes to infinity, just like the stick of gum rule. So what I'm going to do is I'm going to make this entire fraction into a bunch of little fractions that resemble the stick of gum rule. And the way that I'm going to do that is I'm going to do that by multiplying by a variation of the stick of gum rule. Now, the stick of gum rule is 1 divided by x, but you could do anything like 1 over x squared, x to the third, because all that's going to do is make this number increase faster, but that will just end in the same result. So in this case, my problem has x squareds as the leading term. So I'm going to say, let's multiply everything by 1 over x squared. And when I do this, I am going to make sure that I am writing each piece of the problem in its own fraction. So this will be like 3x squared over x squared minus 1x over x squared. That should be minus 2 over x squared. Okay, and I'm just going to keep going. Same thing in the denominator, taking each term and putting it over that x squared because I'm multiplying everything by 1 over x squared. All right. Let's, next we're going to simplify. So if I go through one fraction at a time, I would end up simplifying the first one to 3. The middle would be 1 over x, negative actually. The last would not simplify at all, so it would stay negative 2 over x squared. And I'm just going to keep doing this throughout the whole problem, okay? Now, remember that you have limit properties that allow you to take the limit of each term individually when you have a sum, a difference, a product, a quotient, all that stuff. So essentially what I'm going to do, and I'm not going to write all this out because it would take me 10 minutes to do it, but I'm going to show you the first few things. I could take the limit of each of these terms separately, okay? So I could write it as the limit of 3 as x approaches infinity for 3, the limit as x approaches infinity for negative 1 over x. Do you get my point? Rather than writing it all out, I'm just going to do that with you. Hopefully you're okay with that. It's just too tedious of a process. So now I'm going to actually take the limit. Okay, what is the limit as x approaches infinity for the number 3? Well, this is a constant value, right? So constant values are unchanged. So that means the limit, no matter where I'm going, will still be 3. What about the limit as I'm approaching negative 1, or as I'm approaching infinity for negative 1 over x? Well, doesn't this look a whole lot like my stick of gum rule? It sure does. And if I know the limit as I approach infinity for 1 over x is equal to 0, then negative 1 over x is not going to be any different, okay? Or you could think of it this way. What's negative 1 divided by an infinitely large number? It's basically like 0, okay? So this is going to go to 0. Okay, what about the next part? What's the limit as x goes to infinity for 2 over x squared? Well, if you have a really, really big number down here on the bottom and you square it, it gets even bigger. And then you take 2 and you divide by that really big number. Again, you're going to get something that's pretty close to 0. So if you look, anytime you have a whole number on top and a variable on bottom like x or some variation of it, that limit is going to go to 0 if you're plugging in a really infinitely large number. So you're going to end up going through your limit process and getting a bunch of zeros in it, which is kind of what we want because we want to get something that's computable. So if I simplify this down, I'm going to get a limit that's just equal to 3/5. Okay? Now, there's a shortcut. Okay? Are you ready for this? The shortcut is going to involve you actually thinking through about what's important in this function. And what's important is that you understand that there are pieces of this rational function that drive and kind of control the rest of the function. So if you look at this, I am taking infinity and I'm plugging it in. And I'm taking it and I'm squaring that number and then subtracting infinity and then subtracting 2. When I square a really big number and then I just go ahead and subtract 2, that's not going to change much, okay? So whatever the highest degree term is in your function is going to control the entire function because it's the most powerful part of the whole equation. Does that make sense? So in this numerator, 3x squared is going to do all the work because all these other two terms are just very small and sort of insignificant. So I'm going to kind of focus on the part that has the power. And 3x squared is the most powerful thing on the top. Same rule goes for the bottom. What's the most powerful driving force here? It's going to be whatever has the highest power, in this case, 5x squared. Now, I can do sort of a factor and cancel situation with these two terms because they're both the most powerful terms on their respective side of the fraction. So let's go ahead and cancel what they have in common. And now we're left with just 3/5, which is the same answer we got doing it this long, crazy way. Okay. We're going to try that again here, but this one is going to require some algebra before we can get to the taking the limit part. So in this problem, I am going to start by, I would like to be able to just plug infinity in, but this one's a little tricky because when you plug in infinity and square it and then take the square root, it would just kind of be back to infinity, and then you have minus infinity. So it's kind of a weird thing, and I can't really wrap my head around what's going on. So I'm going to instead put this whole thing over 1 and create one of those conjugate situations where I'm going to multiply the top and the bottom by the conjugate, okay? And my hope here is just to make something that looks different than what I'm dealing with now, because what I'm dealing with now is a little confusing. So we're going to make it look a little different. So if I do the conjugate, I'm going to get x squared plus 1 minus x squared on top. And then I would have this radical thing on the bottom, okay? I'm going to simplify the top, and then I should be ready to look at the limits step. So the top's going to be just a 1, and then I've got this denominator that's remaining unchanged. All right, now why don't you try to look at the limit again? So I am not going to do this the long way. I'm going to suggest that you try just the logical approach, and that is just thinking about what's happening if I plug in a really big number for x. So if I plug in a really big number for x here and here, I would get, let's see, infinity squared is still infinity, add 1, still infinity, square root, still infinity, right? If I add infinity, what's that mean the bottom is? Please don't say to infinity, because that's not a thing. But it's just a big number, right? Still a really big number. So essentially what I'm dealing with is I'm dealing with 1 over some really big number. Okay? We've had this situation arise before. And 1 divided by a really big number is going to take you to a number that is really close to 0. So 0 would be your limit. Okay? This is an example of a composite function. So I want to remind you of the limit properties we learned a while back. Those are if you have a function f and then there's a function g plugged into it, you are allowed to move this f function to the outside of the limit, allowing you to take the limit of one function at a time. So I'm going to actually take the limit as x approaches infinity for 1 over x. And this is identical to the stick of gum rule. So we already know that this is going to go to 0, right? When I have that answer, I then will bring down the sine function and I will simply evaluate what's left. So I just need to know what is sine of 0 to solve this, and sine of 0 is 0. So that would be my answer. Okay. What about the limit as x goes to infinity for sine? Okay, so we would need to know what the sine function looks like. Sine function starts at 0 and kind of goes up and down in a wave pattern like this. And that's an odd function, so it repeats in a diagonal symmetry of sorts. So what would you say the limit is as x approaches infinity? Well, if I go along my graph, I go up, I go back down, I go up, I go back down, right? Because it's a wave. So are you really approaching anything, or are you just kind of riding the wave? Yeah, you're not approaching anything. You're just kind of riding the wave. So this one we would say, I don't approach anything because I just keep going up and down on this wave pattern. So this one is going to be D and E. And you could say to yourself that the reason is because this one oscillates. oscillates between two values, meaning it just keeps moving back and forth. And remember, sine has a min and a max of -1 and +1, so you're oscillating between those two. So you don't have an answer for that. Okay, what about these two? What happens when I take the limit as x approaches infinity for something like x cubed? You could do this two ways, guys. You could think of the parent function and maybe draw that and kind of read the parent function graph, which looks like this, by the way. Or you could just think logically about what happens when you put a really big number in and cube it, right? If I put in a really big number and raise it to the third power, it's just going to equal another really big number. So we would call that infinity. What about if I plug in negative infinity? Does that change my limit? Well, if I take a really big number and raise it to the, really big negative number and raise it to the third power, I'm actually going to get a really big negative number as my answer. So x cubed has a limit of positive infinity on the right, but negative infinity on the left. Okay, I think I just have two more examples for today. Example 10, I'm going to kind of go through this logic thing again and give you some ideas for how you can break this up. But first I'm going to say, let's try that whole plug-in chug situation. So if I were to plug in infinity and square it, I would get a really big number. But then how do I subtract a really big number, right? Isn't that kind of confusing? How do you subtract two levels of infinity? It's a little bit messy. So what you may want to do instead is you may want to try to change the look of this, because subtraction is making that confusing. So maybe what I'll do instead is I don't know, what can I do algebraically with this? Well, I can factor out an x, right? Do I know that this is really going to do any good? No, not really, but I'm trying to just make it look different so I can actually just do something with it. Now, what I can do once it's factored is I can break this up and take the limit of each factor separately. And maybe that'll help to look at one thing at a time, right? Let's see. If I say what's the limit as x approaches infinity for x, well, that would just be infinity because x would keep getting larger. What about if I approach x minus 1? Well, plugging in infinity and subtracting 1 is not really going to change infinity. So then I end up with something like infinity times infinity. Now in my head, that makes more sense than doing infinity minus infinity, because how do you subtract a really infinitely large number? This makes sense to me because I can multiply two numbers that are infinitely large, because it's just still going to give me a number that's infinitely large. So try playing around with the algebra and see if you can make more sense of it like this. Okay, last one. Here is another problem that looks like a fraction. And so when I have problems that look like a fraction, you can do it the long way, where you multiply by the stick of gum rule, or you can use logic. And when I say use logic, that means look at the driving force in the numerator and the denominator. So what on the top is more powerful? X squared, right? So x squared is going to control what the numerator does, and minus x or negative x is going to control what the denominator does. So we're going to take a look at just those two more pieces of the function because they're the most powerful. Now what we're going to do next is we're going to simplify before we actually take our limit. So we're going to simplify, and this looks like it's going to be the same as negative x if I simplify, right? Because I can take an x out of the top and the bottom. Now we're in a place where we can evaluate the limit. So if I have the function negative x and I plug infinity into that, I am going to get negative infinity as my solution.